Okay, good morning, ladies and gentlemen. Thank you very much for this nice introduction. Thank you for having me here today. So actually, I wanted to exactly describe my profile, but it's already done. Thank you very much. So as you heard, I specialize in fast time resolved method of temperature measurement in nanoscale. So if we energize nanostructure, I then can follow its thermal decay back to base temperature with unprecedented resolution approaching 1 nanosecond. So this is the best result in the world in this sense. So this is one field of my studies, and second, which emerged quite recently, is coming from the fact that I found that with my method of temperature measurement, I can also be very sensitive to the presence of superconducting vortices, and this allows me to manipulate superconducting vortices in nanostructures. So I will try to guide you step by step into not so obvious methods, maybe, because the main physical parameter which I measure in my experiments is probability, and you will see that this probability allows us to extract the temperature of the system and also get an idea about the vortices. And okay, so let's start. So this is a teaser, and just to have some hook at the beginning of presentation. We have very simple nanostructure. You see, this is the single layer polycrystalline aluminum, 30 nanometers thick. The bridge here in the middle is called Diem nano bridge. It is 60 nanometers wide. It is type of the Josephson junction. It has the property that when probed with the current, it switches from the superconducting to normal state at some well-defined, maybe not well-defined, but at some current, and this switching is probabilistic, but okay, this I will explain later. And here is the example of functional superconducting nanostructure, which is very simple, but it exhibits very rich physics. This is just aluminum. You can go and do it in 1 hour in your lab, yes? But here, this bigger enlarged part, it's capable of trapping vortices. So when this structure is cooled down across the sea, we can trap superconducting vortex here, and then with this bridge we can sense the presence of the vortex, single vortex in this box, and moreover we can actually push this vortex out of the box. So when we talk about the sensing and manipulation, the field, the proper field to deal with such devices is vortex electronics. So it aims at monitoring and manipulation of vortices to present new functionalities like memory cells or logical elements, and I will show you that this is actually a very functional, very rich device. So here, if we measure the critical current relation of such device as a function of magnetic field perpendicular to the structure, you will find a series of cusps or suppressions of the critical current. So here, close to the field equals 0, we have the Meissner behavior, meaning that supercurrents, they try whatever they can in such structure to repel the magnetic field outside of the box, but that at some magnetic field, it starts energetically favorable to accept first one vortex, then two vortices, one in one box, two in other box. So these are results of Ginzburg-Landau simulations. So these are maps which you can calculate. This was done in cooperation with some of my collaborators from University of Antwerp. But this measurement shows you here this very kind of rich characteristics, and this is very reproducible. This onset of first vortex entry and next vortex entries, it always happens at well-defined magnetic fields, and this huge suppression is result of in fact of the, this is the effect of the expulsion of the vortex from the box. So this is just I will come to back this in more details later. So now I will introduce you to how actually I measure such curve. So this is what I do. I measure switching current, which is close to critical current. Critical current is defined as the one at which junction, this bridge, switches from the superconducting to normal state. So to do this, I sent on the bridge series of many pulses, say 10,000 pulses, and in response to each pulse, the junction may switch. So switching means the transition from superconducting state to normal state. Like, just pay attention to this blue curve. You see here that supercurrent branch means 0 voltage, although there is some current flowing through the junction. But when we cross some threshold value of current, the bridge tells no, I can't keep more superconducting current, I have to switch, and this is, okay, this is technically we call it switching. So then when I send close to the switching threshold many pulses, in response to each pulse, the junction may switch, but it doesn't need to switch. Switching has probabilistic character, so we talk about the switching probability. And this probability is defined by the number of times junction switched divided by the total of number of pulses that were used to test the junction. And this is how we can now talk about switching current as the one corresponding to half switching probability. So this is the basics of the switching protocol. And we can measure with this method. Okay, here you can see that I have boxes of different sizes. The width of the box is given in each panel, and also the double or single boxes. And for each of them, dependently of width, I can see that the entry of the first vortex at the value which is inversely proportional to the width of the box. So the wider the box, at smaller value of the magnetic field the first vortex enters. And these are also here also present studies for the superconductor, just for wires. For wires, these traces, they are fully reproducible. They have kind of much more intricate characters, since here we talk about the entry of row of vortices. This is not just single vortex entry, but we get at certain magnetic field threshold, we get many vortices entering here. Okay, so then here the kind of message is that when we sweep this magnetic field, we see some features on these curves at well-defined magnetic fields. And now we can try to think why it happens, why such why these features appear. Here we have comparison of theory with experimental data. Experiment is presented with blue solid curve, and these dots correspond to Ginzburg-Landau simulations. And Ginzburg-Landau simulations, shows you that the curve can be considered in such sections. So each section corresponds to certain occupation of vortices in these boxes. So, for example, here the first section contains no vortices. This corresponds to one vortex. Here you have 2 vortices, and so on. And Ginzburg-Landau simulation predicts always that when each next vortex enters into box, then we see increase in the switching current. And this is because when such vortex enters here, it reduces the Meissner screening currents in the box, and this in turn enhances the superconducting order parameter in the vicinity of the bridge, and then the critical current is also slightly enhanced. So this is the message that we get from the Ginzburg-Landau simulations, but the physics is more rich, so not always we see the enhancement of the critical current. Sometimes we see actually the suppression. So you see here we don't have the growth, but we have the decrease of the current, and so the characteristic is more rich. And I will argue, and I am quite convinced now with this interpretation, that this is due to dissipation, which is not taken into account in Ginzburg-Landau simulations. Okay, so for those of you, because I realized that maybe there are also some chemists in the audience and some people who are not familiar. So this vortex, what we are talking about, you can think that this is some typhoon of supercurrent, like you have some tornado which circulates around itself. So the vortex is this means that we have supercurrent flowing around this core. Core is normal, so here we have the it behaves like normal metal, but around we have just this supercurrent circulating, and this is what we mean by vortex. This is quantized object because it contains exactly one flux, well-defined magnetic flux inside, always flux quantum or multiple of flux quantum. So so we play with some quantized objects. So then the point is that here we sense the different configurations, and we have control over. Then in the next slides, I will show you that I have actually control over the existence of this vortex, so I can push it out and I can trap it here. And then this kind of box you would consider as the unit memory cell. So when you have no vortex, it is logical 0. When you have vortex, it's logical 1. So then you can test it with the switching protocol, and when you find that, okay, there is vortex there, you have the switching current corresponding to one value. When there is no vortex, to another value, and this is the philosophy behind the construction of some operational device. So now, okay, this is to show you that the entry of the vortex is very predictable as a function of magnetic field. So this is simple formula which has kind of intuitive character. So it tells you, you can tell all this beta p over 4, it's order of unity. But this is the value for first vortex entry. So it tells you that when the flux threading the box, this square, approaches phi naught, this is this quantized unit of magnetic flux, h over 2e, then actually it's more favorable for the vortex to enter, and it appears in the box. So this is it arises as a compromise between the Meissner state and the normal state. So we get this type 2 superconductivity in which yes, we have the mixed state with the vortices appearing in the system. So this is the threshold value, and now we can put here both simulation and experiment with open and closed symbols on this plot, and you see that it follows nicely this relation, and this is okay. This can be considered even as a kind of calibration. So if you want to get the entry at given field, you just need to select the proper width. So it's very reproducible in this sense. Okay, and here I will focus now on the one particular curve, which are also displayed before, but now I would like to see in details what happens here. So you see, we have, if we focus now on first, second, third, fourth vortex entrant, we enlarge. Sometimes we see the enhancement of the critical current on the first vortex entry. Sometimes it is reduction. So Ginzburg-Landau simulation, as I tried to explain, always predict this behavior. And this is the consequence of the reduction of Meissner screening current and enhancement of the order parameter in the vicinity of the box. But we find, like, for example, for this transition number 3, that first it goes up, but then it goes down. And it turns out that actually this is the predicted behavior by Ginzburg-Landau, but here, the second vortex, which is captured here, it is expelled during readout. So when we try to measure the critical current, before we actually come to the point, we measure with pulses, yes? So before we come to the point when this bridge switches, first the vortex is expelled from the box, and when it's expelled, it creates dissipation, it creates quasi-particles. So this box is heated. When it's heated, then the critical current changes. It's very sensitive to temperature. And this kind of suppressions are a result of dissipation appearing when we push vortex out of the box. So okay, then I will come in next slides that actually we can measure such dissipation when we move single vortex out of the box. So we can measure dissipation arising from manipulating one single flux quanta in the box. So now I'm going to make a short detour, and then we will come back to these devices. I would like to explain to you the method of this fast temperature measurement. So this is very well suited for heat flow. So okay, so I'm now doing the tour, and then we come back. So this method is very well suited for investigating various heat flows at nanoscale, so we can measure the fundamental thermal processes of electron-phonon coupling. So this is when you have hot electrons which are at low temperatures, which they exhibit their own temperature, which may be in general very different from lattice temperature. And then we can investigate energy exchange between electrons and phonons in the same metallic chip, or we can investigate the exchange of energy between phonons of the nanostructure and phonons in the substrate. We can investigate the propagation of phonons in the substrate. We can investigate the diffusion of hot electrons or absorption of phonons, blackbody radiation. So for all this, to study these processes, when say electron system loses energy or gains energy, then its temperature changes, so we can sense it with thermometer. And this kind of investigations were done in steady state so far. But if you want to get the kind of very deep access into understanding of them, you need to have some dynamic tool, and this is where my thermometer comes to play. So I will give you an example. So let's consider such process in which here we have heater. This is copper island, 1 by 2 micrometers. And we send short pulse. This is 4 nanosecond pulse, which hits this box. The rest of the structure is made of aluminum. So the bridge is placed 60 micrometers away from the heater. So when we hit this copper box, we create quasi-particles. They go through these necks and they start diffusing in the wire. So it takes some time for them to arrive to the remote bridge. Yes, so we expect that at this point that the quasi-particle population it should go down in quasi-exponential way. But at this point, we expect 60 micrometers away that first we should see no signal, and then after some time, the signal should pick up, come to maximum, and then go down. And this is, okay, and now we ask question, actually, what is the time delay? How long it takes for these quasi-particles to arrive from here to here? And, okay, so to do this, we will use the temperature dependence of the junction. So if we measure the critical current of the junction, you will find such dependence. Here is the critical current as a function of temperature. So you see that it shows quite good sensitivity above 0.3. Okay. Alternatively, you can measure for the constant testing current. You can measure the variation of the probability with temperature. So here we probe the junction all the time with the same testing current amplitude, but dependently on temperature, we get different probability. So this too you can consider as a calibration curve. So whenever you measure 0.6 switching probability, you tell, okay, my temperature of my system is 408 millik, or okay. So these are two methods of the measurements which you can do, and then to get the dynamics, you employ this pump and probe protocol, which is familiar from laser physics. So first you send the heating pulse, and then sometime later, you ask your system, okay, what is your time now? So during this short testing pulse, which sets the temporal resolution of the measurement, the junction must decide whether it wants to switch or not. And this switching, the value at which it switches depends on temperature. So the method addresses perfectly repeatable thermal processes which can be restarted many times with the same initial conditions. But once you have such system, which you can restart, say, 10,000 times, you can very well reconstruct the temporal profile of temperature. So let's apply it to our system. So to this example that I displayed, yes. So we do exactly like this. This system has this property because I send here the pulse and then I measure I check what is the probability, what is the probability of the switching for the bridge. So measurement of the probability involves sending always many pulses. Just think about tossing coin. If I ask you what is the probability to obtain tail for the coin, then you have to perform maybe 10,000 experiments to give me a good number, yes? Because otherwise, measurement of probability always involves measurement over ensemble of the same, statistically the same systems. And here, this is what we do. So we energize and send pulse, energize. So each sequence of pulses is like one tossing of a coin. So this is the result that we get. You see here that this is the probability, not normalized probability. So 8,000 is 0.8. So we measure how many times the junction switch, and you see that first at delay equals 0 between the heating and testing pulse, we have some interference of two pulses. So they just they are imposed on each other, and we see some crosstalk. So this is just allows us to calibrate the timing of experiment. But then there is no signal on the bridge, meaning that quasi-particles has not yet time to arrive to detector. Then signal picks up, it reaches maximum after 300 nanoseconds, and then it goes down. And we can recalculate now this profile into temperature. So this is this blue curve. So you see that this corresponds to increase in peak. It corresponds to increase of temperature of 14 milli-K at the base temperature of 400 milli-K. And now we can check whether this is the expected time. So if we compare it with Einstein's Smoluchowski law of diffusion, here it gives you this squared distance can be average square distance is just the time of arrival of this maximum multiplied by diffusion. So if we know the diffusion, we expect that the maximum should appear after 280 nanoseconds. And this is what we find in experiment, the position of this maximum 300. So we can either treat this result as a confirmation that the method really measures nicely, or we can tell that this is the direct measurement of the diffusion of electrons in aluminum. Okay, so this is the one of the example of the thermometry. Here I have okay, these are profiles measured for different temperatures. So when we increase temperature, you find that this peak becomes lower and lower, and this is due to fact that electrons, quasi-particles, when they travel from the heater to the detector, they are annihilated on the way, they emit phonons. So this is due to electron-phonon coupling. And then if we increase temperature even further, you see that at 0.8 K, actually there is almost no signal left, but still it is measurable, this red profile here. So we can measure increase of the temperature smaller than 400 microkelvin with the resolution better than 100 microkelvin. Okay, so this is really both, it shows very nice temporal resolution and also very nice vertical resolution, temperature resolution. Okay, so now we are coming back to the first part of the talk. So we want to use these methods of the temperature measurement to study these vortices. So let's now consider again this box. So you see the point is that when the vortex, this is the Ginzburg free energy of the vortex inside the box. If field is sufficiently, magnetic field is sufficiently low, there is no stable energetic minimum for the vortex to be here. So as in physics, okay, we can analyze this energetic point of view, but when we start adding more field, then some local minimum first local, then global establishes, and it means that this is exactly this threshold field for which it is energetically favorable for the vortex to sit in the middle of this box. And this is one feature, so it tells us that, okay, when we cross this threshold field, we trap the vortex. But there is also a second feature, that this energetic landscape can be tilted with application of the current flowing through the box. And this, physically, this is understood as an effect of the Lorentz force acting on the vortex. So the current flowing here, it exerts the perpendicular force pushing the vortex to the side of the box. And energetically, it means that our energy landscape is tilted. And it also means that upon exceeding some expulsion current here, I wrote it IXP, that it's possible to actually to get rid of the vortex completely, to remove it. So we can apply, physical picture is such that by application of short pulse, we just open the barrier, and we create short time window for the vortex to escape. It escapes, and then when we close the barrier, it's not anymore here. So we create kind of metastable state. And can we accomplish it in experiment? So now we have such sample. This is prepared in such a way that the field at which one vortex enters is quite, okay, it's still quite low, but for these examples, it's quite high, 5 millitesla. And we measure, so it nicely, the first vortex entry corresponds nicely to this calibration curve that I showed you, but we see here the pronounced dip. And this pronounced dip is due to the fact that the vortex, we can expel this vortex close to the field at which it was first trapped. So then when we increase the field further, the trapping potential becomes here deeper and deeper and deeper, and then actually it's impossible to apply a reasonable current which would be able to tilt the energy landscape to extent that we can get rid of the vortex. But so we find a narrow range of fields in which we consider that the expulsion of the vortex is possible during readout, during driving the junction to close to the critical current threshold. Okay, and now we will focus on this, we will magnify on this dip and see what happens there. So if it is so, we first look, so the black curve is the magnified curve from the previous picture. But now we do a trick. We apply to our protocol. Okay, so here is our protocol. Reset means that we hold the structure above TC. So we exceed 1.3 K, everything is boiled, and then the system cools down back to its base temperature. So this is, okay, this is initializing pulse, annealing pulse, resetting pulse, whatever, but its aim is exactly to prepare system always in the same, statistically the same initial condition. But then we add one more pulse, which we call Lorentz. So its intention is not to switch the junction, because the black one is to test the junction, but this one is lower than the switching threshold, but we just try to get rid of the vortex. And you see that if we, okay, here I just present the one curve with 120 microamp Lorentz pulse, short pulse. And if we apply this pulse here in this sequence, we find that actually it's possible to recover this peak, which means that we extended the Meissner state towards higher field values, which means that here there is, for this curve, we have vortex during readout. Here we don't have vortex during readout. Here we have vortex, and when reading out the bridge, we expel it, we heat it, and that is why the critical current is lowered. Here we don't have vortex, so when we probe the bridge, there is nothing to be expelled, so we don't heat. And we find quite big, I mean, this is a rather huge difference in critical currents of these two configuration, with vortex and without vortex. So now what we can do, we can actually scan at a fixed magnetic field. What we will do, we fix magnetic fields, okay, 4.4 in the region of this tip, and we ask question: what is necessary Lorentz pulse value actually to the how high should be this pushing current to get rid of the vortex? So you see that for sufficiently, if we don't apply this pulse, which corresponds to Lorentz pulse equals 0, then we measure low value of the current, and it is exactly what I explained, that this means that vortex is there, and we push it out during readout, we hit the system, and the critical current is low. So I showed you that the bridge is sensitive thermometer. So when we expel vortex, we hit system, so temperature goes up, and the critical current of the bridge goes down. So this is this point. Then when we apply some, okay, we start to increase this value, and we see that nothing happens. So obviously this pulse is too low to do anything to the system. But then suddenly it goes up. So this is the threshold value at this given field for expulsion of the vortex. So once vortex is expelled, we hit system, and then we wait long time for everything to thermalize back to base temperature. And now when we measure the critical current, we find high value, yes? So you see two states. Okay, so this is the basic also of the logic. We have 0, 1, 0, 1. So now, okay, what we do, we will now play some movie. Let's try to do this, okay? So this is the Ginzburg-Landau simulation. I want you to convince you that this is not only my kind of crazy interpretation, but it's well supported in this Ginzburg-Landau simulations. Here is vortex sitting. This is the box, and now what we do, this is fixed magnetic field, and what we do, we start to ramp up the current going through the bridge. So this is just current going here. Look what happens to the vortex. So we still start tilting the energy potential, and the vortex slightly goes to the side. You see it's displaced from initial position. And still we go up with current, okay, it's shifted, but it doesn't go away. And at some point, okay, now we keep constant current, it goes away. This is the expulsion of the vortex, which I was talking about. Yes. So current goes here, and then the vortex is pushed by Lorentz force perpendicular to the flow of the current. Okay, then there is some intricate process of phase slip. So yes, okay, so let's go back to the presentation. Okay, so we now what we want to do, we want to investigate this process of pushing away vortex at different magnetic fields. So we'll get this kind of, I call it vortex stability diagram. At first, it may be kind of confusing. It looks nice, but this is, okay, I will try to explain it. So here is magnetic field. Here is Lorentz pulse. We use again the same protocol. And this curve, you just try to go for fixed magnetic field. Low, up, low, up, low. So this is curve which I already showed you here, yes? This is the cross section of this map. So this shows you that sufficiently low magnetic fields, we are in Meissner state, no vortices. Above this magnetic field, we can trap vortices, but also we can expel them. So here we apply this Lorentz pulse, and you see that for zero Lorentz pulse, we have low value of the expulsion of the switching current. And when we increase the Lorentz pulse, then we come to the threshold value at which we start expelling vortices. So here we can expel, and then this border corresponds to actually to the switching threshold of the junction. So we can't go beyond here. So when we apply Lorentz pulse, which is higher than the switching threshold of the bridge, then we switch the junction, and this has an effect of annealing everything. Okay, so here this curve, okay, this one is onset of the first vortex entry. Here you have two curves which are cross sections of the vortex stability diagram map. So you see here is up, then it's low, and then it recovers up again. And here it goes up, and then it goes down. So in principle, this gives you the full information about this simple box. So it tells you what expulsion current you have to apply at given magnetic field. So if I want to, for example, if I work at this field and I want to expel vortex with the Lorentz pulse, if I apply this value, it's too low. If I apply here, it's okay. And dependently whether I expelled it or not, then during readout with the testing pulse, I will find my system in high or low state of the critical current, yes? So now what we do, we will just apply this protocol for one point here. So what we do, okay, we apply such Lorentz current pulse value. So we expel vortex. And then what we do, we want to see what is the dynamics of the temperature of the box after we expel the vortex. So you see, this is the usual relaxation experiment, which is depicted here in the bottom panel. This is the pulse sequence that I use. So I reset system, I expel the vortex, and then I ask, what is your temperature of the bridge? Yes, so you see that here this delay sets the time lag between the testing and the expulsion. So here we have, okay, this delay. So of course, to get each of these points, I have to send 10,000 pulses. This is this probabilistic measurement. But at each delay, I measure the switching current. And you see that after I expelled vortex, look, this is logarithmic scale. Here is 1 nanosecond, 10 nanosecond. This shows this is really state-of-the-art measurement of temperature. You will not find such perfect resolution in solid state with any other method. So here now the switching current, critical current of the bridge, it recovers back to the initial value. So this is the process of relaxation of quasi-particles in the box after the vortex was expelled. We can recalculate now this critical current into temperature with this calibration curve that I introduced at some point. So you will find that just after expulsion, the temperature of the box, this small nanoscopic box, goes up by 225 millik, from 400 millik to 625. And then, okay, and then it's so this is roughly exponential decay, but it is in logarithmic scale, it looks like this. So you can fit in linear regime the tail of this dependence. You get 400 nanoseconds. At this temperature, it corresponds exactly to the electron phonon relaxation time expected for overheated electrons. So if you overheat electrons in your system, then it takes so much for them to equilibrate back with phonons. So it remains in perfect agreement. And now this temperature increase, actually we can recalculate into, if we know the heat capacity of the aluminum, this I assume as a value known from literature. So then I can actually calculate the amount of the heat which was dissipated during this single expulsion process. So this is calorimetric detection of a single expelled vortex, and from experiment I get value 310 in minus 19 joules as a result of the expulsion. Yes, and this is value which is very close to the. You can roughly get the same number if you assume second Josephson relation. If you assume that during expulsion of the vortex, you change the phase across the vortex by pi, but this is something maybe more intricate. Okay, so the message here is that we have really the quantized object, because the quantum thermodynamics, in principle, it deals with the manipulation of the heat at a single particle level. So if we are able to push one electron, catch one photon, measure the thermal conductance due to single phonon mode or single electron mode, then we are talking about quantum thermodynamics. So here I extend the notion of the particle to this object. This is kind of artificial particle, this vortex, but it's well-defined quantized object, and we measure the heat arising from manipulating this object. Okay, so I will now. So this was kind of the main result which I wanted to show. This has actually, I am showing this result for the first time. It has not been yet published. So I will now quickly show how many minutes still I have. 10 minutes. Okay. So I will tell you briefly about caloritronics with superconducting vortices. So caloritronics is a discipline in which we manipulate or control heat flows. Okay, this is like the definition which you can find in Wikipedia maybe. So what we do here, we have sample. We have here heater. So always I have, okay, some element of my circuit which is meant to energize the superconductor. So this heater on which I send the short pulses of current to switch this bridge, and then it creates quasi-particles. They start to diffuse here. Now this box is huge. It's 4 by 400 micrometers. So it actually, I can put here many vortices. So when it's cooled across TC, you will find here many vortices. Actually, this is some artistic representation, because these vortices are in fact much smaller than these loops plotted here. So they have this kind of, here is the actual size. Yes. So this is 1 by 1 micrometer. So so the vortex is, say, 300 by 300 micrometer. But here we have huge box 4 by 400 micrometers. So the point that we put here is that we create these quasi-particles, they diffuse here, and then they arrive to detector, and we want to find if this diffusion is affected by the presence of vortices in the box. Because vortices, as I gave you at some moment definition, they contain normal core. So this normal core is the region of the enhanced electron-phonon coupling, and in principle, if quasi-particle gets into such core, it's trapped there. So vortices cores are known as a quasi-particle traps. So they should efficiently remove quasi-particles from the system. So that is why I put here quasi-particle annihilation. So you can consider vortex as a quasi-particle annihilator. So what we do here, we do this diffusion experiment as I showed you before. So here you have, okay, we energize, but now with 100 nanosecond pulse. And okay, they go here, and we test how much time it takes for them to arrive here, and what is the amplitude of the signal. So at magnetic field equals 0, you see that there is actually this is this black profile. But when we add some magnetic field, here it is really, I added in steps of 0.13 millitesla. So the last curve is only 1.4 millitesla. So you see that already adding small field results in suppression of the signal. So first it's suppressed quite fast, but then it saturates, and then you can add more field, but it actually doesn't happen. It doesn't allow you to reduce the signal. It's not helpful anymore. So it looks like to some extent, at first it's very efficient to kill this quasi-particle flux, but then it saturates. And this is, okay, I have some hypothesis that this is due to secondary phonons excitation. So if you are interested, we can talk more about it. But this is just, I want to mention, just briefly give you an idea of experiment. I apply 100 microsecond pulse, and then you see here that as long as I hit on my system, that the current is low, the switching current of the bridge is low, because we have quasi-particles arriving to the junction, which suppress this critical current. So the population of quasi-particles means suppression of the critical current. It means enhancing of the temperature. And again, here for the magnetic field equal 0, the suppression is much more pronounced. So more quasi-particles reaches the bridge, and at higher fields, less of them arrives. And this is also, it shows big tendency for saturation, because there is no difference between 0.6 and 1 millitesla. We can also make more tricky experiment. We can put actually the small box 1 by 1 micrometer between heater and the testing. And now we ask question whether single vortex is sufficient actually to see the suppression of the flux between the heater and the bridge. So this is now annihilation with a single vortex. And the example is presented here. So we have, again, the energizing bridge on this left side. Here you have testing bridge. Distance is 60 micrometers between these two. And in the middle, you have the vortex trap. It's 1 by 1 micrometer. So, okay, you see quasi-particles are here, and they will diffuse here, and they have chance to be annihilated in the vortex core. And those which are not annihilated, they may potentially find its way to the bridge and be detected. So this is more tricky experiment, but still you can find if you measure now the critical current of the detector, you will find that the critical current as a function of field, with field is suppressed. This is the Meissner feature. But then when you this is in measured with no quasi-particle flux without heating. But when we heat and measure the same dependence at times in which we expect quasi-particles to arrive, we see, now we focus here on this part of the plot, which is given in the right panel in an enlarged window. You see that when we cross the threshold field for which we expect the vortex entry, then we find small enhancement of the critical current, of the switching current. So it means that here there is still no vortex on the way, and the critical current has some value. But then when we add this vortex, it helps actually to kill some quasi-particles. Less of them reaches the bridge, and then the effect is that the critical current is slightly higher. So these experiments, in principle, it shows that the sensing of the single remote vortex through the effect it exerts on the flux of diffusing quasi-particles. And perceive it like this. So we just see this, this kind of quantum small object, by the effect it exerts on the flux flowing from here to here, on the flux of heat, flux of quasi-particles. Okay, so I will only briefly now mention this, so you can investigate also propagation of phonons in insulating substrate between two galvanically isolated structures. So this is just, imagine you have one metallic island, this is another, but they are galvanically isolated. By steel thermally, they are coupled through phonons in the substrate. So this process is of very big importance now in some quantum computing and so on, when you have many functional devices on the same chip, and actually they should be cooled down to as low temperature as possible to increase the coherence and so on. But in fact, the dissipation on one on the structure creates also problems for another, exactly due to this effect. So here I designed such example in which we heat the line. Here this is copper heating line, and then the phonons, they propagate through the substrate and they hit this bridge after some time. And then what we see that, okay, for just, this is okay, you see the geometry of experiment. So this is the perpendicular cut of the device. So the current flows perpendicular to the plot. So we hit this structure, then it emits phonons. They travel through the substrate. They are bounced off of the back surface and they hit the detector. And actually what we see here, we measure the enhancement of probability due to creation of quasi-particles due to these phonons hitting the sample. And this onset, this time given here with star, corresponds exactly to the speed of sound in silicon. So it tells you how much it takes for the ballistic wave to travel from here and go back to detector. Okay, so I am ending my presentation. So here are my collaborators. This is my very good friend from Institute of Physics. We create kind of tandem. We work together. We have been working together now for almost 10 years. And this is my PhD student. Another PhD student is Priya Singh. I have to add her photo. I have a good collaborator in Finland and also recent collaboration with Antwerp University. I would like you to invite. I would like you to invite you to our web page. We created recently channel on YouTube. So this is Cool Phone Group, and you can find some the recorded presentations of our group there. Okay, funding. We are funded by Foundation for Polish Science, National Science Center. European Microkelvin platform also helps to travel to Finland. Okay, and these are publications relevant to the current talk. The first one is devoted to it describes this method of sensing vortices with superconducting nanobridge, and other are related to this fast time resolving nanothermometry. Thank you very much.
Thank you very much for such a comprehensive work. Now we have some time for questions. Do we have the questions from the audience here? We have one. Just wait for just.
Thank you very much for a nice talk, and I have more than one question, but ask many. The first very natural question is: you use aluminium of certain thickness,
yes,
and you have this width parameter. So is this general parameter for any superconductor, or this is only for the aluminium of this thickness that you use?
Width? What do you mean
the
width?
Width of this vortex square that like trap, the vortex trap.
Okay, so this is quite universal. It contains no material parameters. This yes, if you consider this plot, yes. Okay, this one you see.
Yep.
So it should enter. It's here. It's yes. It should be not material dependent. So you could make it from other other materials also. But I have not verified whether it's satisfied. This is for aluminum verified only.
Okay, so now then you show the two traps and how you repair the vortex and maybe how it can be worn back. And then you have a current flowing in one direction. Is this like stochastic? You know which trap the vortex will appear or will be dissipated?
If I have a double trap of the same size,
exactly,
I don't know. Then I don't know, because it's actually, first I thought that it's better to have such symmetric traps. It's like this one. I don't have the point is that, okay, if you create just the same, then it's difficult really to, because of the symmetry. Yes, it's difficult. So then some details, some fluctuations of the surface or of the edges may decide to which one the vortex enters first. So first I thought that having two symmetric is better, but now I play with single. I think it's better, because then this is exactly, we know where it goes. But for example, here you see this is double trap. So you see this double feature here, like 1 and 2.
That was my question heading to. So
yes. So this is, so it means that one vortex actually enters to second box slightly later. So there is some cross, some spread. But this can be also that when we have one vortex in one box, then we slightly change the physical setting for another to enter. But they enter very close to each other. And also when you look here, okay, like this obviously arises. This is the situation in which you can expel first vortex because second has not yet entered. Then here you can't expel the first one because it becomes stable. And then the second enters and it's not yet stable, so you can expel it. Or here you can expel two simultaneously. So the signal is actually doubled.
And for the experiment of the Lorentz field, then you had the asymmetry in expelling the vortex. What would be the origin of the asymmetry?
This is actually, I don't know actually. We are so this shows this kind of diode effect.
Yeah, exactly.
Yes. So I don't know. I would be happy to understand it. So I must say that we are looking for the explanation at the moment.
Okay, thank you.
Thank you very much. Do we have some other short question? Okay. But you need to wait for me for the microphone.
Hi, thank you. For my question is, what is the critical magnetic field to producing a single vortex?
Sorry, sir. Could you speak louder? Yes.
What is the critical magnetic field to produce a single vortex in your case?
Yes. So this is this is the calibration curve that gives you. So this gives you the formula. So it's roughly phi naught magnetic flux quantum h over 2e divided by the area of the box.
So how much it is exactly?
So it tells you that, okay, in considered experiments, it ranges from 1 to 12 millitesla, just to enter first. Yes, like you see here. Yes, for example, here, this is the entry of the first vortex. Yes, this is what you are asking?
Yes. So
yes, so this is the field for which the vortex is captured for the first time spontaneously when you cool down the structure across Tc. So this is field cooling. Okay, so what we do, we apply magnetic field with weak magnet, but we do annealing, fast annealing on a chip, sending these annealing pulses. Because structures are so small, the structure is so small, you see, that you can switch the bridge and then you overheat everything above. Actually, I know the thermal effects quite well because this is what I studied for last years. So this temperature of, although the global temperature of the fridge is say 300 millik, this you can overheat in nanoseconds to 2 or 5K easily. And then when it cools down, since the magnetic field is on, it is field cooling and the vortex spontaneously is trapped. And yes, so this you can find this calibration curve, okay, in this paper also. But it's kind of very intuitive meaning, because you see that the phi naught, when the flux which you apply covering the area of the box is such that it is flux quantum, then it becomes energetically favorable to accept one vortex into trap.
Okay, so what is the beta in this case? Beta?
Beta is phenomenological parameter, because this formula is strictly valid, should be strictly valid for wires. But we found that for wires, we need some additional multiplicative factor, which is 1.7. And for boxes, since they are more strongly confined, it is 2.45. So this is phenomenological factor, which is necessary actually to explain the experimental data, because, okay, this formula is valid for wires. I mean, okay, it should be valid for wires, but there is this additional 1.7. Yes.
Okay, so there is any critical magnetic field formula for like multiple vortex, like 2, 3, or 5? So is there like any formula like this to?
Yes, so for next vortices, it's roughly, they will enter it at multiples of this flux, roughly. So like you see here. Here is maybe, okay, it's not exactly periodic, but if you want to find the approximate value, you can expect the next entry at the double field compared to the field at which the first vortex entry happened.
Thank you very much.
Thank you. I have just last question about, because you were showing this box is symmetrical where you keep the vortices. Is there any work which is like more like a triangle? So when you send the current from the left to the right side, it becomes different, or hydrodynamics of electrons?
Yes, this is a very, very good question. We have it. I could show you in my lab book, in my notebook, in which I put the ideas. I have the idea actually to replace this box with triangle to investigate the effect of this asymmetry of this diode effect. Yes, so we expect that just by changing the geometry. You see, what is very nice about these structures, the protocol which I explained you, it may be not so intuitive because we measure this probability, but you have to think that about this tossing a coin, then it becomes simpler. My junction is a coin. And the probability of obtaining head for this coin depends on the state of the vortex box or on the temperature of the box. So this is the coin for which probability can be changed with various parameters. But otherwise, to fabricate the structure is very simple, you see. So I don't need to do some very crazy topological materials to arrive to nice physics.
Yeah. Very nice. Thank you very much. We need to finish the discussion now. We would like to thank you very much again.
Thank you very much.